Hello, everyone. Welcome back to another exciting lecture of options, futures, and derivatives. In this video, we will be covering the first half of Lecture 10. The topic is model-free results, and it relates to option pricing. Model-free results are going to answer the following question. How accurately can we price an option without making any assumptions about the distribution of the underlying stock? That is, we'll write that down so we know the motivation. How accurately can we price an option without making any assumptions about the distribution? Another way to say that is model of the underlying stock. Okay. How accurately can we price an option without making any assumptions about the distribution of the underlying stock? Remarkably, it turns out that we can say a great deal about option prices without any explicit distributional assumptions, and these are what we generally call model-free results. In the first half of the lecture, we will learn about two important model-free results. The first is that we can derive upper and lower bounds on call and put prices for European options. The second is that we can generally describe how option prices change when we change certain contract parameters, such as the style, maturity, and the strike. In the second half of the lecture, we will learn about something called put-call parity. Put-call parity relates call and put prices to one another. It's one of the most important results in option pricing. And we'll end with a brief summary. Okay, let's get down to the nuts and bolts. So to really understand the need for model-free results or where they come about, we need to first recall some facts about the forward price from lectures 3 and 4. So the main thing we need to recall is that the forward price, the no arbitrage forward price, was completely determined by no arbitrage and law of one price arguments. To find the forward price, we simply created a replicating portfolio that consisted of the stock and the bond. And what we noticed was that the payoff of this replicating portfolio exactly matched the payoff of the forward at the future date, capital T, regardless of what the stock price was. By law of one price, these two portfolios had to have the same value at date zero. And so the value of this replicating long stock, short bond portfolio had to be equal to the value of the forward. And this gave us our no arbitrage forward price, which was beautiful. It's in closed form. F0t equals to S0e to the RT. Okay. The important thing about this derivation is that it required no assumptions about the distribution of S. So it required no assumptions about distribution of the stock price at the later date. Okay, it could be log normal, could be all sorts of shapes. Okay, uniform, etc. Okay, all we need to know were the relevant frictions. Was it frictionless? Was there dividends? Was there cost of storage? And we could calculate the no arbitrage forward price. We want to now ask, is this also true for option prices? Okay, is no arbitrage enough or do we need more? In general, the answer is going to be that we need a lot more. The exact pricing of options requires assumptions about the model or the distribution of the underlying asset at the later date, the random variable. However, it turns out that we can say a lot without pinpointing the stock, the option price exactly, just through this no arbitrage argument. Okay, so we can't find out what the price is exactly, but no arbitrage will allow us to impose general restrictions on the option price, especially in the form of inequalities. Okay. The first restriction that we can impose is lower bounds on option prices. Okay. In particular, European option prices for calls and puts are both bounded below by zero. Both the call price, C0, and the put price, P0, must be positive. Why is this the case? Because there would be an arbitrage if it did not hold. If these prices were less than zero, there would be an arbitrage. And the reason why is because remember that both calls and puts have non-negative payoffs. Okay, so if the call price less than zero, then there is an arbitrage because what you have is $100, the form of $100 lying on the ground. Okay, if the call price is less than zero, you receive money to take the portfolio. And if you take this portfolio, you never pay anything out. So it's by definition an arbitrage. The same holds for a put. Okay. The second model free restriction that pops out of just no arbitrage is that call and put prices for European options are bounded above. The call is bounded above by the stock price today. The put is bounded above by the strike price today. Why is this the case? Let's think of a put first. Okay, so think of a put payoff. It's equal to the max. This is at the later date, capital T, K minus ST and 0. Okay, this put payoff is always going to be less than or equal to this maximum amount, K. Okay, so the best we can do is if the stock price, okay, drops to 0. And what happens if the stock price drops to 0 is that the strike price is what we get paid out. So the maximum put price, just like in our example of Bear Stearns, is the maximum put payoff, just like in our example of Bear Stearns. It's bounded above by the strike. So the put price at date 0, this happens at date T, the put price at date 0 can be no higher than this maximum payoff. Okay. For the call, we have a similar argument. So the call payoff at date capital T is the maximum of ST minus K and 0. The best case scenario is when the strike is 0, which means that the call has exactly the same payoff as the stock. So the call payoff, the best the call has is the payoff of the stock. So the call should always cost less than or equal to the stock. It's inferior to the stock in the sense of the payoff, so it must always cost less than. Okay. If either of these bounds are violated, so if the call price exceeds the stock price, there's an arbitrage. You buy the stock, you sell the call. If the put bound is violated, then you buy the bond and you sell the put. Okay. The final restriction, or it's more of an observation, is that we can actually do better on the lower bound than just saying it's greater than or equal to 0. We can impose a tighter lower bound, and that lower bound is that both call and put prices must be approximately greater than or equal to the present value of their intrinsic value. Okay. This is approximate because it doesn't always hold, but that's the way you can interpret this interior payoff that has the S0 in it. Okay. So without making any assumptions about the distribution of the underlying stock price at the later date, we can bound call and put prices above and below. This is going to give us approximate ranges for which calls and puts can fall. We'll then need to form an explicit pricing model to locate the exact price. So this graph highlights this concept. The graph is going to plot the range of permissible prices under no arbitrage for a European call option. On the x-axis is going to be the current stock price today. This will all update 0. On the y-axis is going to be the call price today. The solid blue lines represent bounds on the option prices. The blue shading represents the set of feasible or no arbitrage option prices. All the prices that agree with no arbitrage. Okay. Note that the call, let's translate our mathematical bounds into this graph. The call price here is going to be less than or equal to the stock price. And this blue line on the top just plots a 45-degree line in which the call is equal to the stock price. The bottom blue line represents the lower bound. Okay, this was the feature that the call is greater than or equal to the present value of the intrinsic value. Okay, so the call is bounded above by the stock price today. The call is bounded below by the hockey stick shaped intrinsic value present value. The call price can belong anywhere in the light purple shaded region. Okay, prices within this range do not permit arbitrage, but without a model, we cannot exactly pinpoint where it should be. That is, if say we have a current stock price today of S star, the call price could be here, the first X. It could be that second X. Okay, we cannot tell. We know it falls somewhere along this line, but we cannot tell exactly what it is without making any distributional assumptions. However, we went from the range of possible values, being this whole payoff space, to now just this trapezoidal region. Okay. This graph shows the same concept or ideas for puts. Okay, on the x-axis again is the current stock price. This time on the y-axis is the put price. Solid red lines represent upper and lower bounds on the put price. Red shading is the set of feasible model prices that do not permit arbitrage. The put is bounded above by the strike price. This top red line up here is the line in which P0 is equal to K. It's at a height of K, it's a horizontal line. The put is bounded below by this hockey stick line. Okay, this hockey stick line is the one in which the put option is equal to the present value of the intrinsic value, K e to the negative RT minus S0 and 0. Okay. Prices within the shaded region do not permit arbitrage. So if you had the current price of S star, then prices, any two prices within this range, say this X or this circle, neither of these prices permit arbitrage. They're all consistent with model-free results. However, we don't know exactly which is correct option price without forming an actual model or distribution. But we can narrow the payoff space to this whole XY region to now just this shaded region right there. Okay, so that wraps up the subtopic on pricing bounds. This told us or gave us general restrictions on where call and put prices can belong without violating no arbitrage conditions, but it showed that without making an explicit modeling assumption, we couldn't arrive at exact option prices. In the final part of the lecture, we will not derive exact option prices. This will be for lecture 11. What we will do here is we'll start looking at something called comparative statics. Comparative statics are going to describe how option prices change as we change their input parameters, especially with respect to style, maturity, and strike. It's going to be called comparative statics. Okay, and we're going to establish 3 facts using these comparative statics. Okay. The first fact is that American options are worth at least as much as European options. The price of an American call, which will denote C0 USA, on a stock S with a strike of K and a maturity T, is at least as large as the price of an otherwise identical European call, which we will not superscript with USA, on stock S, maturity T, and K. So these are an otherwise identical European and American call, but the American call options price must be at least this as large as the European call options. And the same exact thing applies for American puts versus European puts. Why is this the case? It's because, recall from the last lecture, American options are more flexible than European options, and any strategy that can be implemented with a European option can be implemented with an American option. However, there are some circumstances where you might want to exercise an American option when you couldn't do so within a European option, and this is going to give the American options value. In cases where early exercise is never optimal, such as calls on non-dividend paying stocks, though, this will be a strict equality. The second fact of comparative statics is that longer maturities are not always better, but they usually are. Okay? In most cases, okay, an increase in a maturity is going to lead to a higher price. But in some cases, you're going to actually get the opposite result. Okay, so these equations say essentially that the price of a call, this European call on a stock S with a maturity T prime and a strike of K, can be greater than or less than the price of a call on the same stock with the same strike with a different maturity T, in which T prime, the maturity on the left-hand side, is greater than the maturity on the right-hand side. Okay, and the same is going to apply for a put. Why is this the case? Well, in most cases, I should say, the relation that's going to hold is the greater than relation. In probably 99.5 or 99.9% of situations, increasing the maturity date is going to increase the value of the European option. Okay? But there are going to be some specific examples in which a longer dated option is worse. The main example for the European put could be the Bear Stearns examples of less than. The main one is a put option on the Bear Stearns stock that we considered with the current stock price equal to 0. Okay, in this case, the shorter dated put was more valuable. Dated put more valuable. Okay, because didn't wait as long for payoff, okay, of the strike. Okay, but in general, what's going to happen is that this potentiality value is going to usually be much larger in terms of the maturity. It's going to be much more valuable than reducing it. Okay. The third and final fact is that call and put prices change with respect to the strike. Call prices are going to decrease as you increase the strike. Put prices are going to increase as you increase the strike. Why is this the case? Okay, so the mathematical way we say it is that a call on a stock S, maturity T, strike K1, is greater than or equal to a call on a stock S, maturity T, strike K2, whenever the strike K2 is greater than or equal to K1. The reason why is that you just think about the payoff to the call at day capital T. It's max ST minus K and 0. And this goes down, okay, as K goes up, and it goes up as K goes down, holding all else equal. Okay, so call payoff holding all else equal is higher when the strike price is lower. And so if you have a K1 that's less than some other K2, then this call is going to be better. Okay, put price is the opposite. Put on stock S, maturity T, low strike K1 is going to be less than or equal to put on stock S, time maturity T, high strike K2, high strike K2 greater than or equal to K1. Okay, reason why again, put is equal to max K minus ST and 0. So the put price is going to go up as K goes up. Okay, so higher strike puts are going to be better, and it's going to go down as K goes down. Okay, the put receives K, so K up is good, and the call pays K, so K up is bad. Okay, call prices increase as the strike decreases. put prices increase as the strike increases, but they do so in a convex fashion. Okay, you don't have to really worry about this, but in general, they're increasing or decreasing at a convex rate. Don't pay too much attention to this slide. Okay, so that wraps up the first half of lecture number 10. In the second half, let's summarize first what we did. We looked at no arbitrage pricing balance. We basically said how far can we get, or how precisely can we price an option without making any assumptions other than no arbitrage. We saw that we could bound option prices above and below. This gave us some nice, cool graphs of the regions in which it's feasible for call and put prices to exist. These are all European options, but we weren't able to pin down the exact price without a specific model. We then looked at some comparative statics. We learned American options just using a no arbitrage assumption are at least as good as Europeans. The maturity is usually increases the call and put prices, but some rare cases it doesn't. And call prices increases the strike decreases, put prices increases the strike increases as well. Okay, in the next half, we'll learn about put call parity and a summary. And then lecture 11, we'll get to the really fun stuff of actually getting the exact option prices. So let's take a quick break. We'll resume the lecture in the next video.